start.
You know, 64, 65.
There we go. There we go.
As I was mentioning, it was quite a battle to get it to be announced.
Tim, did Ray Duncan from LMI ever hang out with FIG? Or is he just off on his own?
Well, you know, I don't remember. Maybe in the really busy day, 84 or 83, when we have thousands of people gathered together.
You have microphone?
I do.
He does. He should be talking.
You should be hearing my voice.
Say something again?
You should be seeing some signal from me.
Yeah, I think so. I think we are.
Okay.
That's hard.
Somebody's talking anyway.
Oh, no, we're not.
You need a receiver and a transmitter.
We actually have to have
CQDX.
that in there. Now try again.
Does that work now? Any different?
I think so.
Should be more extreme signal.
Yeah, I think so. It's still. I think it still sees me, but audio. Where are we? Headphones. Okay, we're on.
Kevin, how sensitive are you to the schedule?
We're only 6 minutes. Go. You are alive.
Take a breath.
You are alive.
I'm Carl Klonsch. I'm here at SVFIG. I'm going to talk about the IBM 1130. This is a machine that's really near and dear to me. It was the first machine that I got hands-on access to, so I could really step through and see how the computer was working, look in some detail. And, as a result, I've always loved it and wanted one. And when I had the chance to pick up a real one about 3 or 4 years ago, I went out to Kansas to pick up this particular machine you see here, truck it back, and it's now in my garage working. So let's look a little bit at the 1130 first.
Was it working to start?
Sorry?
Was it working to start? Repeat the question from the internet.
So the question was it working at the start? So I had to do a few things to get it working, but it wasn't too many things that had failed. The main circuit breaker failed half off, so there were a few kind of oddball things, but it came up pretty quickly, a few weeks. So the 1130 was a machine that IBM thought up for a new market segment. Back in the 1950s, late 1950s, they decided to go after what they called the small scientific market, which was computational intensive tasks at a very low price point. And so they were aiming at things like small engineering groups, small scientific projects, computer-assisted design, universities, chance for students to learn software on the machine, and they launched the first model of that called IBM 1620 in 1959. So that was originally designed out in New York at one of IBM's major labs, but they transferred that out here to San Jose. The San Jose group fostered, kept that machine going, and then developed a second generation called the IBM 1130. So that machine was announced in 1965. Now, if you know the history of IBM's computers, that was an odd time for that to be launched because in 1964, IBM announced the System 360. And with it, they brought out a mythology. The mythology was, it was one architecture for every kind of workload, scientific, for every size of machine. Everything would be a compatible single series. And they immediately afterward had to in reality, show that wasn't true. There was no way they could reach the price point for this small computationally intensive market with a machine that was driven by the 360 architecture. So the first machine they were allowed to announce was the 1800. It's really the same processor, but it had a lot more I/O. And the I/O really for sensors and actuators, because the goal was to do process control. So many chemical plants, power stations, traffic lights around the world were powered by IBM 1800s. But when they finally fought their way to an announcement in 1965, given the totality of 0 orders for 360s from their market segment, the machine became a market. And there was one other version that you'll occasionally see that IBM gave a different model number to. But it was really, the difference was the software and peripherals. It was focused on computer-assisted education. So some of the early CAE systems. It was implemented using the same technology base that IBM had developed for System 360. So in the upper right, you see a chip, a little piece of ceramic. It's not a chip, it's a piece of ceramic that's essentially a one-sided PCB. And on it, IBM put discrete transistors and diodes and resistors. Those were then sealed in a metal can and stuck on a slightly larger, this time, regular PCB, which is the module on the left. And those modules in turn went into a larger board, the backplane, which IBM chose to call a board. And the picture on the bottom happens to be a backplane that has core memory stacked in the middle.
There's a
and then all the
microphone. This
support
one.
logic around the outside. So this was a core memory, yes.
What I was saying came up in my.
Oh, to seal it hermetically
saying
because
it's coming up in
the
my
transistor
headset.
was
You got a
sitting
mic
out in
on
the
here.
open, so it would oxidize, so they had to seal it. And rather than each transistor having its own can, it would amortize that. So core memory machine, and the cycle time of that was 2.2 microseconds. So to build a machine in that era with core memory, everything was designed around the core memory cycle. Destructive read and rewrite. So that cycle for core memory access was divided into 8 275 nanosecond cycles. And you could do various things in it. For example, first cycle might tell the memory what address to read. The next cycle would bump the program counter, so it's now ready to pick up the next instruction. So you would accomplish things during those 8 subcycles. And based on that 3.6 megahertz clock, you might get the impression that this was a fast machine. But that's very misleading, because in reality, it took multiple core access cycles for most instructions. It could take as many as 4 of those 2.2 microsecond cycles just to fetch the instruction and figure out the effective address, and then it could take up to 32 more for multiply and divide for complete execution. So in reality, this was more like about 100,000 instruction per second system, which you wouldn't guess from that cycle time. To hit their price point, IBM had to leverage lots of technology and designs they already had. And so they went at it with fervor. So they took the keyboard from an 029 key punch. So if you use an IBM key punch, this is exactly the unit. They just took it out of the key punch. And in fact, because the key punch had a sloped keyboard, the 1130 front has to slope at the same angle, because they didn't even change the keyboard mechanism that much. So we have a sloping front strictly because of that. We have a console printer in the back, which is a golf ball selectric typewriter. IBM had a product line at the time called the 1050 that had a full typewriter with a keyboard called the 1052 that you would have seen with every 360 mainframe as the operator's console. And then a print-only version, the 1053, which was stuck on the 1130. For a printer, they looked at their warehouses, which were full of punch card, pre-computer machinery that had come off lease. And the sort of queen of their punch card systems was the 407 accounting machine. And in that was a printer that would print the results of card transactions. So they just took this printer as it was and wrapped modern-looking sheet metal around it so that they could call it a different product. The low end of the commercial computer range was the 1440, and they had a card reader punch for that, so again, they leveraged that. Didn't even bother to change the numbering to look like it was part of the 1130. But they did develop one peripheral from scratch for the system. And it's because this machine was designed here in San Jose. So San Jose was where IBM developed disk drives. So they saw this as a great opportunity to develop something they originally called RAM kit, for some reason, which is a single platter disk drive with a cartridge. 14-inch platter in a cartridge that you stick in, was 1 megabyte in capacity on the 1130. So that form factor, that single platter, really became ubiquitous in the industry. Digital equipment companies, RK05s, everybody's single platter systems were licensed and based on the technology from RAMKit. For a plotter, they went back to the first generation small scientific machine and grabbed the same plotter. Again, no change to the monolith. In fact, the plotter came from Calcom. So Calcom. So
I work there.
You recognize the 565?
Yes, I do. I recognize everything here.
But just slightly different coloring and all, but same. And then out of that 1050 system, they had paper tape, 1054 and 1055, which were paper tape readers and punchers, and that repurposed for the 1130. If you were a higher end kind of shop, you could use some more sophisticated peripherals from other systems like the 1403 printer, or particularly for graphics and for CAD, light pen-based 2250 terminal. And, I believe that was on the system where Warren was developed. So the architecture of the machine, it's a word-oriented machine, 16-bit word. 2's complement, which means 32,767 to minus 32,768 was what you could represent in one word. But it did have double precision, 2-word instructions. So a little more than 2 billion plus and minus. The main memory was a maximum of 32K words. So you had to be a little careful of what you did, particularly if you were doing anything with large matrices or any other large data structure. It's pretty hard to fit everything in the machine. They used an interrupt system for I/O, so when something was ready to deliver input or the I/O was done, you get the interrupt. But they also developed what IBM chose to call cycle stealing, which is direct memory access that we would know from modern computers. And that was really only used on high-end or expensive peripherals, except for the disk drive. The RAM-kit disk drive used direct memory access. The basis of the machine was a single register, effectively, the accumulator, where you did all arithmetic, all logical operations, and storage. So you would reference storage, do something against the accumulator. But there were 3 index registers for doing addressing arithmetic. And they were memory maps. So that meant anytime you referenced an index register, it required 1 extra core memory cycle to fetch that value. And the way they approached the sort of classic problem with computer architectures of the fact that with a 32K word memory, you need 15 bits for addressing. So if you stick that 15 bits in every instruction, the instruction gets pretty long and wasteful. So their solution was something they called relative addressing. So different systems at the time implemented the solutions different ways. Digital equipment partitioned memory up into what they called banks. And instructions only had a few bits that were all within one bank. IBM with the 360 had registers that were involved in addresses, so there was no limit, but you only needed enough bits to specify which of the 16 registers rather than the full addressing space. But on the 1130, I'll show you how they solved the problem. So first at the top, an instruction had 3 fields that every type of instruction had in common. 5-bit opcode, so 32 major instructions. A bit to tell you whether it was a single word or double word, what they call short and long instruction. And then 2 bits to select an index register. Now in the short instruction, the 16-bit instruction, there was 8 bits left over for addressing. So that's a signed field, which meant you could effectively go 127 words before or after the current instruction. In practice, that was pretty useful because most code tends to be local. And so where you'd branch or the data structures you had quite often could be placed within 127 words. And you could use short instructions for economy of memory. But the long instruction, which is the second figure, had the full 15-bit absolute address in there. So you could address anything you needed to. The machine was based on core memory, upper left, that's the heart of the machine. And so the sort of major registers that you would be aware of as a programmer of the system were these 6. Storage address register in the top middle was the address you were going to read or write. Storage buffer register was the data that had just come out of memory or you were going to update memory with. The program counter IBM chose to call instruction address register, IAR. And then this accumulator I mentioned. Now, you could have double precision numbers, so there was an extension to the accumulator. So first 16 bits, then extension. And that one last register is there because, remember, this machine was one storage address only in the instructions. And so if you wanted to do an addition, the first instruction you'd issue is load. Load would fetch contents move it into the accumulator. Second instruction, add, would fetch the other operand, stick it in here, and then the arithmetic logic unit would interact between these two to do the add, subtract, multiply, divide, or whatever you needed. And I mention that because if you were working on an 1130, developing code and debugging it, you'd be very familiar with those. The left side of the light panel are those 6 registers. So you would see your code step through and what was going into the different positions. And you had a rotary dial on the right, and you would use that to single step through instructions, but you could do it more finely grained than that. You could look one core cycle at a time, so you could see it fetch the first word of an instruction, and then maybe the index register contents, and then see it put away the results. Or you could look at each 275 nanosecond individual cycle and watch things change cycle by cycle. So pretty handy to look into the execution, the design of the machine, and see how it actually implemented a multiply or an add or something else. In this era, all of IBM's machines were batch-oriented. So in their mind, the main way you'd interact with a computer was to submit your work as a deck of cards or paper tape and get output on print or on punch cards. But there were other ways of interacting with it. Of course, the software that they developed for that, the disk monitor system, had the peculiarity that file names could only be 5 letters, and you're all aware of that reality. But you could interact with the machine as well. So you could write a program that would let you use the keyboard, that console printer, and 16 toggle switches on the front of the machine. So you could interactively execute and do interesting things as well. So the machine was designed originally for the small scientific market, so their target languages were Fortran 4 and assembler. But quite a few other languages showed up on the 1130. IBM shipped COBOL, RPG, and APL, wonderful APL, which was something you had to do just from the keyboard and console printer, obviously. But in addition, languages like Lisp, Forth, a subset of PL1 and BASIC were implemented by users and put on the machine. That's pretty understandable if you consider that one of the target markets for this was higher education. And so many universities and other places would have 1130s for people to be experimenting with software and programming. And so the more languages you had, the better. So one of the things about the 1130 that you would grow to know and love was its peculiarities. And there are really 3 of them I'm going to talk about here that would have been painfully obvious if you dealt with an 1130 in person. So the first is the way it did its arithmetic. So IBM was trying to save money. And so they thought, well, it would be kind of frivolous to actually have all the carries calculated when you do an add, because that takes extra circuitry. So instead, the way an addition would work, so if we look on the left, imagine the top blue area is that arithmetic factor register, and the bottom is the accumulator. So we want to add those 2 together and come up with something on the right that's the sum. And if we immediately, we look to the right-hand 4 bits, we see we're adding a 7 and a 1, right? So that's going to involve some carries because the answer is 1000. But the way the 1130 would do it is it would just exclusive OR those 2 to produce a partial sum. And then it would keep track in the AFR of any place that there had been a carry. So how to do that? If you look at the rightmost position of these 2 registers, they're both 1. So that means there's a carry into that position. And there's 2 other places where there are carries. So after 1 round, the machine knows it had some carries to deal with. So it does another cycle, doing the same thing. The sum gets updated, but we still have a carry. And in fact, we have a 3rd carry. So you can see that rippling requires a cycle for each position where a carry has to ripple through until finally we get to the end. There's no more carries, and this is complete. So on the 1130, depending on the data, the time it took to execute was variable. And it could be as bad as 15 rounds of ripples if you had, 07777 and 1, or as fast as a single cycle. So it made it a little difficult to estimate the running time of your algorithms. Second thing that was memorable about it was the disk drive. So when IBM developed this RAM kit, they apparently weren't confident in their ability to position the ARM with a voice coil to the right position. And so they put in a mechanical ratchet. And so instead of electrically moving the ARM and having it stop in the right place, they would just apply force with the voice coil and allow the ratchet to move 1 or 2 tracks at a time. So when you were sitting there, you hear these sounds as the disk went back and forth. You remember that? It's a linear ratchet. And what that meant was anyone who was operating at 1130 got a pretty good sense for where your job was just by the sounds. So you're doing a Fortran compile, it's quiet for a while, then you hear some and you know it's preparing the code for execution. In your own application, there may be several phases and you would recognize that it fetched some things to move to a next phase. So you really got a good sense for what was happening orally because of that grunting. Yeah, floppy drives got that grunting back, but it seems like everyone but IBM went away from the mechanical ratchet immediately, so DEC and everyone else figured out how to do it, and HP and so on. And then the low-cost peripherals. So if this was the line printer, this was the card reader punch, they would eat up almost all of your CPU capacity if you were doing I/O at the same time. And it really elongate your job. And the reason was, to save money in the peripheral, IBM put all the work on the CPU. So if you're reading a card, you would get interrupted 80 times. Columns here, read the column. Columns here, read the column. Worse for the printer. So the printer had wheels with 48 characters around it, rotating. And it would interrupt 48 times, once for each character, and saying, okay, CPU, you're about to have a D. And the CPU would have to scan the print buffer 48 times and then set up bits to say which hammer should fire. So that was pretty cumbersome and time consuming as well. So anyone who could argue for the increase in budget would go for the higher performance peripherals that gave you back some CPU. So that's it in a nutshell. I tried to get through the content and answer questions. Right.
And one of the graduate students in the astronomy department was running this. And I mean, because it's just, that's how because the door remains
so that the web can hear it.
Okay, sorry, let me come over here and you can say it again so the web can get you.
Because we're a little pressed for time.
Right, but it's interesting because that's where the console was. The plotter would be to the right, and then behind you was the drive, that had, gigantic frisbee, and the same thing with that, the line printer.
Yeah, it tinkled too.
Yeah.
This weird tinkling
God,
sound.
I'm just sitting there going, I just remember that. It just. And the reason why I like going down there, that was basically the astronomy department's reading room, because the graduate student there, who was the department chairman, he said, okay, if you're in the department, I'll put your job, your deck job in there, because, oh God, the hours I was down there.
So I wanted to mention that Carl's looking for a fourth for an 1130 because he's got one.
And since Forth was originally developed on an 1130, and I would have been perfect to have the original software, but...
If anybody here or anybody out in the World Wide Web knows of such a thing, let us know about it. The other thing is that we're contemplating a project to write FIG Forth or some other Forth. Your choice if you're going to participate. We'll reach a consensus on what we're going to do, and then we're going to go do it. Respond to the emailing list, or if you want to just send direct to me, I'm Kevin Appert. I'm on the agenda page. If you can't find my email address out there on the agenda page, that's the way life is. We're going to have to do it without you. So, thank you very much, Carl.
Oh, you're welcome. Thank you.
Grab your computer if you want something like
Okay.
that.
Perfect.
Which,
Give me a calculator and the answer is
which do you want?
You have to be able to think about what you're doing.
Right there.
Does not matter. No, no, I'm fine. Does not matter. What are we doing here? What are we gonna do? How do I do this? I'm not sure.
I don't think so. My copy of the actually wrong. It had a couple like examples.
Oh, that's me. It's not really what I wanted to show yet, but we want to go to here, Hangouts. There we are. Now we start a video call. Come on, Jack, where are you? There he is. Okay, now start a video call. There you are. Come on, start a call.
Line went away somewhere in the middle. So
Yes, I was on the wrong microphone. I found the switch to switch microphones.
You're awesome.
I don't know about that. But
Well, it's the dancing
what do we
bear
got?
effect.
It is the dancing bear effect.
So much better than dancing bear.
Now we want to go. Hangout video call. Oh crap. Okay, so that's not going to work. We're going to have to switch over to desktop. Jack, are you there? Can you hear us? I don't get your video. That should be speakers. Are you there, Jack? What's happening? You hear me, I do not hear you. Now that's speak again, Jack. Can you say? That's me. Speak, Jack, and I'll see. Do I get dots? Yes, I get dots from you. You appear to be speaking, but I am not putting anything out. What the heck is going on? Now we are that way. This should be actually working. Hang on. Desktop. Now try speaking, Jack. Nothing. Nothing. I only see your picture, not your video. Your video is not here. Is your video enabled when you came in? Did you come in as a video call? You think so? Well, okay. Probably the gear up on the upper right-hand corner. If you press that, that will say what your video source is for the Hangout. Camera light is on. Oh, I don't know why this doesn't work. And right now, there. Okay, try clicking your camera on the bottom. Clicking the camera on there's three: microphone, phone, and camera. Try clicking that once and then again. And the camera light goes on and off. So but we practiced, Jack. Speakers. Let's try speakers. So that didn't help.
These guys that wanted their telemetry drawn, they stick the bit on the left of the page. It's like, no, that's not how you do it.
What's wrong? try saying something again. And no, I've got nothing. Why do I have nothing? Okay, let's disconnect. Hang up the call. There, we're now hung up. Let's start a video call again. Well, hang on, let me go try something else at the moment. What do I have? I'm not getting anything now. Okay, answer. You called. Click to join the video call. Click to join the video call. Answer. There we are. But I still don't have any audio or no. Still don't have video from you. Can you hear me? The thing says that I probably have audio, but it's not happening. I'm going to take off the mic at the moment. seconds. Okay, now we have the mic is back working, but I don't have you.
Hello, hello, hello. I'm here. What do you think?
I think all we can do is what we've got right now.
What is that? What
Which
do you got?
is my computer speakers.
I've got voice on the web.
You have my voice,
Your voice on the web.
but not Jack.
Hello.
Voice. Say
Hello, hello.
hello.
Oh, you do?
20 seconds ago, yeah.
Okay, cool. Then this is as good as we're going to get right now. Let's go for it.
Roll your chairs up.
Okay, is it clear? Because it's kind of crackly over here. How's it sound over there? Does it sound fairly understandable?
That's what the video looks like, though.
Yes, for a moment. That'll go away in a bit.
I believe you.
Maybe. Such a foolish person. And now we have, we've got a good picture. Excellent.
Okay. Well, I'm surprised the lens doesn't break.
No.
So.
Okay. Go for it. Talk.
Okay, so when I moved out to Colorado in 1988, and pretty much the last speech I heard from Chuck, or maybe it was when I came out to California for the standards process in San Diego or in Monterey at the Silomar. I came out a couple times, but around 1988, 1990, Chuck got up to speak, and he said that the standards process was crystallizing what Forth had been. But for him, he said, Forth is for me more of an approach than a specification for a programming language. And that was kind of like, cold water on the standards people. But there's a lot of truth in what he said. As a matter of fact, it's all truth. A lot of the things that matter to us when we're young don't end up mattering to us so much when we're older, and our affiliation and our branding on our jackets isn't as important to us later on as it was when we were young. And the C versus Forth war is over. C1, and then in turn, like Sparta having defeated Athens, was overrun by everything else that came after it. And all that stuff turns out not to have mattered, and the exact syntax of the language turns out not to have mattered. But what remains is something like Christopher Isherwood and Aldous Huxley called the perennial philosophy. And that has stuck with me all throughout the 30 intervening years since I came out to Colorado and stopped being able to attend FIG meetings in Silicon Valley. I still tell people about going down to HP at Wolf and Prune Ridge and how we would go in there in the springtime and the building was surrounded by jasmine, and it was like, if you remember, it was like the poppy field in The Wizard of Oz. You just about passed out from the dreamy aroma of the jasmine that they had planted around that building, right? So, Einstein once said about relativity that when explaining relativity, everything should be made as simple as possible, but no simpler. essentially is kind of what I got out of the whole fourth experience, and which has stuck with me and pervades my practice and my methodology and heuristics for solving problems to this day. The problems I solve are vastly different than the ones I was solving 30 years ago. I was solving problems in embedded control. Now I'm solving problems of large business systems for companies, you know, with annual turns in 10 or 11 figures. It's a very different set of problems, but the same approaches tend to yield the same sort of results. It's kind of, to drop back to Chuck, it's kind of funny how prescient he was in sort of a, you know, sort of a mad prophet kind of way. A friend of mine who had attended an early conference in, I think, 1982 or 1983 had attended with Chuck, and Chuck had said, see all these people buying spreadsheets, they should be writing their own, he told them. And that was very funny at the time. But the truth is now, when you go onto you go onto Google, you basically are writing your own spreadsheets. It's almost like you are. That's what computing has turned into. People are given on the web little pieces of tools, and even people who are not terribly expert in computers are able to weave together applications out of them. Another thing Chuck said, I interviewed him by phone around 1990 for another you know, magazine. It wasn't Dr. Dobbs. I interviewed him for another magazine, and I forget what it was. I'd already interviewed him and a lot of people like Mitch Bradley for Dr. Dobbs around 1989. And then 1990 or 91, I talked to Chuck on the phone for another magazine, and he started talking about the future of computers and the network, and he said people are going to be surrounded by little devices that talk to each other, he was saying. And that sounded kind of, you know, like visionary, kind of funny at the time. And now, of course, you know, we have the Internet of Things. He was right. He totally saw that. It didn't help him get rich. It never did. It never, you know, the people, the great visionaries frequently, you know, are not the ones who profit off it. Some of you might recall that I published a two-part interview with the late Lotfizadeh, the inventor of fuzzy set theory, which became fuzzy logic in the Japanese cameras and the Japanese metro and all that. And he mentioned that. He said, you know, people have made billions of dollars off of this. I'm happy that I just got my salary as a professor at the University of California, Berkeley. So the visionaries don't necessarily reap. One sows and another reaps, as the Bible says in its infinite wisdom. But the approach, the approach that informed Chuck's practice had a lot to do with the results he got in terms of being able to see what was going to happen in computing. Another funny thing he said to me in that same interview in 1990, he said, Intel has forfeited the future, he said. Now, from a financial point of view, that's pretty funny, you know, because Intel continues to make reams of money while turning out defective processors. And he said, Intel has forfeited the future. All that complexity, it can't be managed. And we see that now in the meltdown Spectre bug. That's exactly what happened. The architecture of the processor became so complex that no human mind can comprehend the architecture. It takes teams of people working together, and they have to trust each other and play whisper down the lane. And the end result is that the whole, following the same guidelines for managing this infinite complexity, it turns out this same, and reading from the same playbook, all the processors, it's the power processor, the mainframes, everything, they all took the same factoring. Of course, that became a big buzzword in computer programming later in terms of how they teach it to young people. Factoring, factoring, factoring was the chant during the 1990s. And of course, you know, Chuck was the complete master of the concept of factoring long before it became as fashionable in the didactic department of computer science. Another thing I got from him very early is the the fellow called the bazaar versus the cathedral. That book that coined the term open source to go beyond the simple free software concept that was being peddled by Richard M. Stallman. The bazaar is bewildering. There are so many choices. Where do you go? I began to feel this pounding on me in the early 90s. I explored C, I explored C++. I became very proficient in those languages and small talk and on it goes. And what has stuck with me from all those times, I did some very wonderful C++ stuff that I'll talk about in a second. But what has stuck with me from that time is the simplest tools I took with me. And the rest of them, well, I used them when I had to, and then they just sort of dropped out of my practice because I was able to achieve what I wanted to achieve with simpler tools. The templating system in C++, I don't know how familiar any of you gentlemen are, or ladies if there's any present, with C++ templates. I was at the company they call TPC in the movie The President's Analyst with Lee Marvin. Was Lee Marvin or James Coburn? I was working at TPC, so to speak, and I had a huge project to do, and their problem was that they had voicemail and they were trying to write custom voicemail applications. It was taking them 3 months to write the simplest application and deploy it, and they said, fix this. And I created a C++ library that totally was informed by my fourth practice. It was linguistic instead of numeric. You just gave phrases. You typed all the function name, all the member function names were phrases, and they were very, very memorable, and it handled all the numeric stuff behind the scenes and just totally encapsulated it in a very linguistic approach, like Forth always did. Forth did not have a notational approach, it had a linguistic approach. And that was good for me because I was never good at notation. I could do complex math, but the notation always defeated me. I never could really keep straight the precedence of operators and stuff like that. And Forth discarded all that, and I discarded that from the libraries I wrote for people. And they went down from 3 months to 3 weeks to deploy an application. And in the course of it, I had to deal with the C++ template system as, Rogue Wave was defining the standard template library at the time. And this was Solaris, and this was the Solaris C compiler with their implementation. And basically, the template library did not work. It simply did not work. You could not do the full scope of what templates were promised and had been promised since the early 1980s, and this was like 1999. And still templates didn't work because C++ was too darn complex. So along the way, somehow I picked up M4, the macro language, which has been around on Unix since 1974, 1975, and it's still there. There's still GNU M4. And it's sort of like Prolog, except without the database. It just resolves macros that are resolutions of macros that are resolutions of macros recursively. And instead of using templates, I used M4. And so I wrote a recursive makefile that first processed the M4 code and generated the C++ code for all the protocols I had to use. Because there are about 150 different message formats and about 300 different kinds of parameters in this protocol to the voicemail system. And it was just, it was totally, I was able to do what other people hadn't been able to do, and it really was because I would home in on simplicity instead of fashion. One fellow at the time asked me, how do you have this grasp? How do you get to the heart of the problems? And I said, it's because the first thing I learned in computing, and I learned around the fourth crowd, is to be a computer programmer, you have to know how computers work. You really have to know how they work down to the electrons crossing the semiconductor. And you gotta get about that far and know everything between there and up. And that's the other element of Chuck's approach. Chuck really knew how every piece of everything worked, from what he did down to the metal. He focused on essentials. And I have a book here. It is possibly the 7th or the 12th copy of the book that I've owned. You can see it's falling apart. It's a paperback. It's not very well kept, but it's Merle Miller's Plain Speaking, the oral biography of Harry S. Truman. And Truman was a man who applied to politics the perennial philosophy that was preached by Chuck. Here's a comment by Dean Acheson, about who was his Secretary of State during the Korean War and all that stuff, back in his second term in office, in his one full term in office after he was reelected in 1948. Acheson, who was educated at Groton and Yale, and had a little mustache and wore a vest and a bow tie and stuff, and was a very, elite Easterner and very unlike Harry Truman. But they had almost a love relationship between the two of them, and they worked together marvelously. Acheson said, I have never known a man who kept so clearly in mind what were first things. Mr. Truman was unable to make the simple complex in the way so many men in public life tend to do. For very understandable reasons, of course. If one makes something complex out of something simple, then one is able to delay making up one's mind. And that was something that never troubled Mr. Truman. And I see this in practice. And to this day, I'm helping a development team currently, and the development team simply will not drop back and say, we don't understand this tower of software we're dealing with. We have to go back and explore the lower levels and make sure we understand them before we try to progress at the top levels. I mean, how easy it is for a fourth programmer to understand their frustration and why that they can't advance. And the cure is so simple, and they won't take the medicine, is that they have to stop pretending they know things they don't know and drop back to the simple layers and learn from the bottom up approach, like the approach in fourth, and figure out what they're doing. I find it everywhere. Chuck came from the mainframe world. In the mainframe world, you find the IBM VM operating system, and the classic IBM VM operating system crowd, who's older than us, and all retired now from that era. They had the same approach. When I got into IBM and started using IBM VM on the mainframes, I said, this is like fourth. Everything is just factored down to its simplest. It's designed for programmers. It's designed for people who want simple tools that fit together nicely. Everywhere you go, you find the same thing. So, as we watch the computer programming field evolve, we see cycles of things. We see that, we started off. We see it go back and forth. We see that we started off with one level of directories. Everything was in the same directory. And then they made directories, and they made deeper and deeper and more complex directory hierarchies. And then everybody said, we can't find anything. We have flattened it out. So they came out with LDAP, so you can find all resources at the same flat level. It goes round and round and round. And each generation rediscovers the same things again. So I had the privilege in 2008 or so to talk to a young fella named Anselm Garba, who's now, he was about 30 then, he's about 40 now, and he's now a big wheel in programming at BMW. He was born in what was then East Germany, and then when the wall fell, he moved to England, and he worked doing computer science. Now he's back in Germany. Like I said, he's a big wheel at BMW, and he runs the website suckless.org. He writes software that sucks less, and he had never heard of Chuck Moore in fourth, really, but he had arrived at the exact same point, and he made some observations to me back in 2008 that I published that I have here on my screen. And Chuck Moore, if Chuck Moore were a C programmer, he would have written this, apply the Unix philosophy, do one thing and do it well. If you design a user interface, make each function only accessible using one interaction approach. Don't you confuse users with doing the same thing in different ways. When you add a feature, try to remove two features. Keep track of your lines of code. The more lines you end up with, the more likely your software is complex, contains bugs, and isn't simple. Never do big changes, always use the evolutionary approach. Only use the revolutionary approach if your existing software is too complex to be fixed and needs to be dropped in the trash. If your software isn't usable from day one, your design is broken. He expanded on this. He said, if you're starting a new project, the first day you do it, it should do something. It should run. You shouldn't sit there writing frameworks. You should write something that works, and the next day it should do more. Data structures are more important than the actual code. Always use the simplest data structure. Never implement or design future extensions. Avoid OO wherever possible. Contrary to common belief, most problems are better solved than not always. Rewrite from scratch instead of trying to fix it. Obviously, Chuck could have written just about any of this. So, I don't think things. Let's see, I lost something here. I lost my notes. Okay. I don't think things have changed that much. I see, I've certainly become, Chuck was a pioneer of open source and free software. He was saying back in the 70s, everything should be distributed in source. Another guy who was saying that was Richard M. Stallman at the MIT AI labs working in Lisp. And Stallman had been introduced to computers at the age of 15 or so by a internship at IBM, a summer internship at IBM in New York City, Manhattan, at IBM, and where they taught him CP67, which became the VM operating system. So all these things tie together in strange ways. All these people who are the prophets of simplicity in design turn out to be among the most productive individual programmers in the world. They turn out to be prophets in the wilderness. The world goes on without adopting their philosophy. Confucius was often unemployed. He was a professional prime minister, and he spent most of his life unemployed, as did his later disciple Mencius, who had never met him but picked up his work about 100 years later. Same thing. But you find that the thought that they had shaped the whole world for the not so great but the good enough. And in my case, that's very much been the truth, that the fourth philosophy has given me a slight edge over my peers in that I know always before we start the discussion what the answer is. If there's something broken, it's because somebody did something too complicated. And if we simplify the discussion and if we get back to first principles, we're going to find where the bug is, what the problem is, what the design problem is, what the system problem is, what the procedural problem is, what the organizational problem is, as we deal with more and more complex and more layered systems and more layered procedures that involve more and more human beings. It's always, if you can get back to the essentials, to what counts, and find your way to simplicity, you have found your way to the solution of the problem. And that's what I've taken from fourth, and that's what's shaped my career for 30 years now. So thank you very much. I managed to put Ting to sleep, I see. So.
Oh, he's awake.
So.
Yes. And
I must
we
have a very soothing voice.
You do.
So.
You do. And thank you for your thoughts. And you got done quicker than I thought you would. We're still ahead of schedule. Any questions? Yes.
I have one question.
When I get up near the computer.
It's this mic. It's this mic. Yes.
So the maintainer of Suckless, I'm quite familiar with his works and his philosophy. Awesome. I encourage every Linux user to investigate the software. What was his reaction when you brought up Chuck Moore to him?
I think he vaguely knew that Forth was there, but he was not surprised. He did not feel that he had personally discovered Steam. He understood that all he was saying was what was, like all the people who are prophets of simplicity, they realize that what they're saying is obvious, and the only thing that is mysterious to them is why everyone doesn't see it.
Mm-hmm. Yeah. Okay. Any other questions? I think everybody's satisfied.
Even early lunch.
Yeah. I appreciate it. I can maybe do some testing.
I'm going to mock Jax for not wearing his SVFIG shirt.
Uh-oh.
You are a ne'er-do-well and a slacker.
I tend to wash them and fold them and put them lovingly in the drawer and keep them forever. I've still got a 1994 Chinese New Year's Grateful Dead shirt from one of the last shows that Jerry Garcia did.
Oh.
Send us a picture of it. But you owe us a picture of you wearing the SVFIG shirt, please.
Okay. I'll take a selfie and I'll email it to you, Kevin.
Excellent.
It's a deal. If you have notes, in particular that screen grab you showed us, do the Linux thing and so on. Throw out 2 for every 1 feature you add. If you could email that to Dave Jaffe, if you can't find Dave, send it to me. We'll put it on the meeting notes.
Right, and that's still online. Dr. Dobbs is gone, but their website is still there, and I don't know if you guys know, but one of the things that happened at the end of Dobbs was that Erickson came down with Parkinson's, and that was one of the things that ended Dobbs.
Okay.
And I was speaking to him for a couple of years. I don't know. I haven't heard from him in a couple of years, but let's see here. Let's do a momentary screen share here. But this article, the conversation with Anselm Argard is still online. So.
Okay.
That's so cool. Send Dave a link to that.
Yep.
Oh yeah.
Okay. Let's see. I forget if I have Dave's address. Let's see here.
Send it to me and I'll send it to Dave.
Yeah. You've got one of our emails, I'm sure. You've got mine, so just send it and we'll get it onto the list. Okay.
Very good.
And thank you very much. And we almost didn't have problems once we got it worked out. Thanks.
Good to see you guys again. Take care.
Yep. Okay. We killed that. We stopped. I think we're set for lunch. We're going out to lunch now.